All right. Can folks hear us on YouTube? Let's see. Okay. Looks like we're live. Well, good morning, everyone. Welcome to another episode of GPU Mode. Today we have Erik Schultheis, who's been one of the most prolific people we've had on the server since its inception, both as an LMC core developer and as someone I think I've seen contribute to the vast majority of working groups on the server. So Erik's going to be talking about int8 tensorcore matmuls for Turing, and Erik also made the request that he wants to be interrupted. He wants this to be interactive. He wants to get good questions. So please ask him good questions. So yeah, without further ado, Erik.
Yeah, so at the very beginning of this talk, one thing I want to really make clear is that the main goal of this presentation is educational. So you're not going to see anything that's state-of-the-art fast or even close to state-of-the-art fast. For this, that's the I think in 1 or 2 weeks, we have the H100 super fast matmul that is doing that. But for this, it's more like trying to get the basics right, maybe. And there, the first question maybe is why do we care about 8-bit integer matrix multiplication, also from the perspective of trying to teach something like tensor cores? And one thing is that this 8-bit integer matmul is actually a very interesting problem, not just on GPUs, but across a very wide range of hardware. If you implement this on a CPU, then you quickly find that it's slightly different than if you do floats, because if you multiply 2 floats, you get again a float. So you have these registers with multiple floating point numbers in a vector register, and then you can just do a fused multiply add addition instruction that combines those. But if you have integers, then if you multiply to 8-bit integers, the result is a 16-bit integer. So there's actually the size of the registers that doesn't match up. So you have to be a bit more clever about this, maybe. And I guess for this reason, also in AVX 512, there's the VNNI extension that gives you a specific instruction that does a 4-way dot product, interestingly, between signed and unsigned integers. So if you want to do, for example, a signed integer matmul, you have to get creative how to use this instruction. And this is quite similar to what you get in CUDA if you don't use tensor cores. There's also a DP for I guess a 4-way dot product instruction that takes 4 8-bit integers of the first operand, 4 8-bit integers of the second operand, does the dot product between those 4, and then accumulates into a single 32-bit accumulator, which has the same size as the original input operands for 8-bit elements. And then, of course, the thing that this talk will be about using them on tensor cores, and nicely they work starting with Turing, so you don't need to have a very recent GPU to try these out. And the second very nice thing about integer multiplication in particular is that the results are deterministic. For floating points, if you reorder your instructions, then the some sort of error compensation or accumulation can happen in rounding errors, and you get slightly different results depending on how you block your operations or how you order your operations. But this doesn't happen for integers. And kind of as a consequence of that, you don't actually have to figure out what are the correct tolerances for test cases. When do you consider an implementation to be correct? When is it incorrect? Do you need to have different distributions of inputs to check whether it also works if the inputs are less well distributed, some extreme values in there? And all of that goes kind of away if you just work with integers, because it's a exact matrix multiplication. So basically what I'm trying to do here is demonstrate the basic uses of tensor cores, and that is directly in CUDA. So no large header library like Cutlass, but also on the other side, not requiring any sort of inline assembly to be written. So just what you get with the regular CUDA toolkit in CUDA C++.
So Eric, maybe a question here, just because like since DeepSeek, I've seen a lot of questions around people having questions around inline assembly. So could you speak to like when is that required versus not?
So any sort of the newer tensorcore instructions, they don't have any equivalent in C++. So for like warp group MMA, for example, I think the only way that you can actually use them is inline assembly. And if you look, for example, in the Cutlass source code and follow all the templates till the very end to where they go, that template also ends in just an inline assembly statement. Though that's also the case for these functions that we are calling here. Like if you look into the CUDA headers, in the end, these things are also just generating the right inline assembly statements. It's just that you don't have to write out the statements yourself, but you get kind of like the nice syntactic sugar on top that the language gives you, like selecting the right thing depending on whether you put floats or ints in instead of having to do that manually.
And is the reason this happens also primarily because like presumably the team authoring the like CUDA C++ APIs like has an inherent lag, or is it just inherently the kinds of things they're representing are not representable with very simple C++ code?
I don't think it's like purely lag. I think maybe the idea is like if you don't want to go super deep, you're supposed to use Cutlass. And if you actually want to have like, you write it really on your own, then maybe you should use inline assembly. Like for any sort of production code, I don't think these functions are really useful. The main use I see in these functions really is to give you kind of like a simple start into using tensor cores on your own. So that might be the reason that I think their value is mostly instructional. And for that reason, maybe they haven't added anything new for the hopper and newer specific instructions.
All right, excellent.
Yeah, okay. And then also the code is only really looking at nice matrices. So very large, and in our test cases, also square matrices, even though that's not really a constraint of the code, but it just means that you can kind of like characterize the size of the problem by a single number. And also these matrices have sizes that are divisible by a large power of 2, so that like you don't have to worry about any sort of like boundary issues. Of course, that's also not what you would have in like realistic code, even though for tensor cores, I think typically even QBLAS requires you to have something like a multiple of 16. But that's really just at the tensor core level. If you want to look at the kernel level, like something that's just a multiple of 16 also is very hard to write because you quickly run into boundary issues. So here we just assume like the matrices are nice enough that we don't have to worry about any sort of binaries. And then, as the title of the talk kind of says, like we are optimizing for Turing, and in this case specifically a Quadro RTX 400, like a TU 104 type GPU. And I can give 2 reasons for this. Like one is simply that if you work on Turing, it has less features, which might seem like a bad thing, but also it means that you don't have to worry about all that complexity, and you can actually get kind of like this feeling of having achieved something that's reasonably fast without having to go too deep into these specialized instructions. And the second reason is simply that we actually have an online submission system where you can try out this kind of exercise, and that's the GPU that the system runs on. So it was the natural choice to use for experimenting here. So, and basically, yeah, this brings me to this next slide. Like since a few hours, it's actually available for anyone to try out. If you go to this website, maybe after the talk, and basically what you get is that you can send your code there, then it runs a pretty comprehensive suites of tests, like not just testing for correctness, but also using compute sanitizer, for example, to check for out of bounds accesses or synchronization problems. And then it runs some benchmark and gives you this table of results, how fast you run for different benchmark sizes, and also a point score based on some rough kind of guidelines how fast you're supposed to get.
So I see a question by Dongyeonju who's asking like, what kinds of efforts are there to optimize a kernel for a specific GPU? So maybe I can rephrase the question a bit to say, like, why is it like there's a few questions like why is it so hard to, for example, write a kernel that can run fast on multiple different kinds of GPUs? And two, assuming you're willing to write like hyper specialized code for a specific GPU, what kinds of things should you be paying attention to?
So I think the main difference is really between generations of GPUs. Like you get quite different types of tensorcore instructions. For example, in Hopper, you get these warp group asynchronous tensorcore instructions that you don't have. So you really, like, if you have like a different compute capability, especially in its major version, then those GPUs are just behaving quite differently, and the compiler tries to hide a lot of these specialties by just reordering instructions in a different way, maybe because it knows that the latencies are different. But there's still quite a bit of like fine-tuning required. But one thing about writing this in CUDA C++ instead of assembly is actually that this code works for both Turing, and I've tested it on Ampere. Even though at the assembly level, the tensorcore instructions are slightly different, inside the CUDA headers, it dispatches to the right type of instruction, and we get the correct code for both. I think maybe it's actually also the same on PTX, and only in SAS it's different. I don't remember exactly. The second thing is specializing for specific GPUs. One thing you can do if you know both your GPU and have some sort of control of the problem size, maybe, then, for example, like one thing that can happen if you're very unlucky is that you have some blocks that are running on your matrix, right? They distribute the outputs that you compute. And then there's exactly the number of such output blocks that you want to compute is somehow not divisible by the number of streaming multiprocessors that you have in your GPU. So at some point, a few of those will be running for longer, and most of the GPU will be idle, but these few stragglers will basically do a full iteration till the end. That's, I think, called tail effect in NCU. And if you know that, then maybe you can like select a specific block size to really optimize for that. Yeah. I think that's more or less the answer at this point that I think makes sense.
That helps a lot. Yeah, let's keep going.
Yes. So anyway, like try it out. Maybe not while I'm talking, but afterwards. And please also give me some feedback. Okay. So now that I've mentioned that we're testing them, actually, like one interesting question is also like, how do you do this kind of testing? Like the simple answer is, of course, just take two random matrices, multiply them together with some sort of algorithm, check the result, and compare if it's the same as the result that the new algorithm is giving you. But that's not really satisfactory for several reasons. Like one thing is just we don't just want to know whether the result is correct or not. We also want to give some sort of useful feedback to fix the error if the result is not correct. And just a Boolean like, oh, this kernel was wrong isn't really helpful for that. And also something like, well, there was a mismatch at index 5733 is not really helping you to debug your matrix multiplication algorithm, I think. So one thing you can do is, of course, look at small matrices where you kind of can immediately see what's going on. But these matrices are so small that lots of kind of like possible error cases that you could get in these tensorcore implementations, they just don't appear because you're not actually covering even an entire GPU block with your small matrix that you can kind of see at a glance. The other idea is to use some sort of special matrices, like, for example, multiply a large matrix with an identity matrix, and then you can immediately see what the supposed result is and kind of check what's happening. And a third option is to have some form of structured matrices. So instead of having like a matrix where each number is different, for example, have blocks of 4 by 4 that have constant numbers. And then you can kind of like map this large matrix multiplication to a smaller matrix multiplication and check where things are going wrong. And going wrong in this case, the most interesting thing usually is like not what's the value that you expected and what's the value that you got, but at which places in the output did you actually see something? Like, is it that if you have a single block, maybe that block is correct, but then if you go to the next block, some sort of like increment is wrong, so the first output is exactly at the block, like the first wrong output is exactly at the block boundary. Like that's the kind of feedback that's probably most helpful for debugging this kind of matmul. And of course, there's also a computational perspective, because if you want to check whether the algorithm is correct, then you need to have like a reference result with a kind of like naive check. But then how do you know that your naive algorithm is correct? Well, you can use a simple algorithm, but a simple algorithm is very slow, and this difference can be multiple orders of magnitude. So you kind of would wait forever for testing the result. And especially for this kind of like tasks that you expect students to do, you might also not want to include a fast algorithm in your kind of like test that is available to students, because that would be spoiling a little bit of the exercise. So another alternative is to use what's called Freiwald's algorithm, which is to use the property that if the matrix C is the product of A and B, then any vector x multiplied by C is the same as if you multiply the vector x first by B and then by A, which is kind of like, if you think about it, what we're also doing in low-Rust, right? Like we decompose a big matrix into two smaller matrices, but then also for the forward pass, we're not reconstructing the large matrix, we are doing the two vector multiplications separately. This, of course, isn't 100% foolproof to detect an error, but it gives you a high probability chance of, if the product is wrong, some output will be wrong, and it's very much cheaper than the full matrix multiplication. So you can actually run this in simple, non-optimized code where you kind of like, just by looking at the code, can check that it's correct. And of course, the third option is just run against some trusted library like QBLAS, which might be the simplest, but then again, it requires, for example, if you give this task to students to download, it requires them to have QBLAS installed, and we try to keep this kind of to a minimum. Okay, so much for designing the kind of like teaching aspect of this. Now, actually, to go to implementing something that does this matrix multiplication. So first, let's actually take like one step back and look at matrix multiplication again with kind of like fresh eyes, maybe. So what we want to do is we have like a matrix A that's m times k, and a matrix B that's k times n, which are 8-bit integers, and the result is supposed to be an m times n matrix, which has 32-bit integers to be able to accumulate multiple 8 times 8-bit results in its output. And then there are kind of like two ways you could kind of think about decomposing the matrix multiplication. The first, and probably the more like well-used one, is bottom-up, that you kind of define just what happens for each single output element in the result, which is just an inner product. And then you have kind of this embarrassingly parallel, if you disregard the fact that memory is a shared resource type of algorithm, which gives you the naive kind of like, oh, that should be n third, not nk algorithm, like so n cube algorithm. You could also think of this, that you can take a large matrix multiplication and actually decompose it into several smaller matrix products. And what I've written down here, for example, is just a kind of like naive decomposition in 8 subproducts. But in fact, you actually can even do that more cleverly and end up with 7 products, which gives you an algorithm that in big O notation is actually faster than this naive algorithm. But it doesn't play very well with modern hardware, so that's why usually I guess it's not used very much.
So Erik, 2 questions. I think I've seen on GeoHot's Discord, he bans people if they use the word Strassen algorithm. But you know, like maybe for a more serious question. So Harsha is asking, is the generation and type of device implementation the right way to reason about what precision is a good choice to run a certain operation on it? For example, if there is support for int4 matmuls, maybe the partial sums are in int32, and this is a bottleneck as you need CUDA cores for this.
I'm not sure what, like the accumulation in int32 2 happens inside the tensorcore, right? Like you don't do that in CUDA cores. So there isn't going to be like a summing of int32. If you use the left algorithm, like if you do this decomposition, like maybe if the question is about the right-hand side, like the Strassen algorithm, like one problem of the Strassen algorithm is that it gives you lots more kind of matrix additions, which in big O notation are cheap, but in actual hardware, they're not cheap. Like these additions you would have to do in CUDA cores. So I think that might be one of the reasons why this algorithm isn't actually used very much. Didn't you have a second question?
No, this was like that was it.
Oh, okay, yeah. So what we're going to do now is, instead of decomposing the matrix into a fixed number of submatrices, we could also think about decomposing it into submatrices of a fixed size. At least if we, from now on, assume that all the matrix dimensions are divisible by 16, so that we don't have any boundary conditions, as I said in the beginning. And then basically think of any matrix just as composed of individual blocks of 16 by 16 numbers. And from now on, we don't ever want to look into what's inside these individual blocks again, because now we can just write down the matrix multiplication at the level of these blocks or matrix fragments. And basically what we get is, again, the naive algorithm, but with much fewer iterations, right? Because instead of like k prime is like 1/16 of k, and the number of I and j indices that you have to get in the C matrix is also 1/16 of the original. And what we have now is that the summand in this large sum, that's exactly the operation that the tensorcore gives you, like multiplying two fixed size matrices together and adding it in a large sum. And what we have to write by hand is essentially like how to orchestrate these sums, how to get the data into the tensor-cores, like the typical problem, I guess, that you have if you want to do anything fast in GPUs. Yeah, and then basically, if you look at just the curator phase, what I said before, like you could use Cutlass for this, but Cutlass also comes with, I don't know how many megabytes of header files. And if you look into the CUDA documentation, the amount of functions that you need for this is actually pretty limited. So there are two different load functions, one store function, a function to fill with a constant, and the last, the MMA sync, is exactly this operation of multiplying the two matrix fragments. And basically, that's it. And then basically these fragments, you can define whether they are the part of A, a part of B, or a part of C. Yeah, the cost you pay for not doing assembly is this warning that's written here for fragment. Like the mapping of matrix elements into fragments, internal storage is unspecified and subject to change in future architectures. So you can't basically exploit knowledge about this to speed things up, even though in the end of this talk, I will show you a way how I think you can do that without running afoul of this constraint, and that actually gives you a noticeable speed up. So let's revisit basically the naive scalar matrix multiplication algorithm, but write it down in a way that the parallels to TensorCore become very obvious. So instead of just writing down the types directly, we define like a result type, which is the result fragment, which in a 1x1 setting is just a single integer, and the fragments of x and y. I guess I'm using x and a and y and b kind of like interchangeable here. Sorry for the notation. Both of these are single 8-bit integers, and then we have a result that we initialize to 0. We have this large sum where we iterate over the k dimension. We load the two fragments, which are single integers, and we do a fused multiply addition operation on this accumulator. And in the end, we store this result. Now, if we want to have like the simplest TensorCore matrix multiplication algorithm, it goes like this. So basically, nothing has changed on the algorithm level. We just define now these 16 by 16 fragment types. We fill it with this fill fragment function instead of equals 0. The loop now goes in steps of 16. And our addressing also needs to take into account that we have steps of 16. And the INJ indices, like the part that you don't see here, like in the beginning of the kernel, they also need to be calculated differently based on the thread and block index. So that like there's 1/16 of these, like you have fewer blocks now. Then the plus equals multiplication part is just this MMA sync instruction. And finally, the result is this store matrix sync. And caveat here, I'm not 100% confident that all the code examples I present are going to work as they are. I've taken them out of the real code and kind of like edited them to fit on slides. So I might have made some typos there and they might not exactly work, but they should get the idea across. So now we've written a nice matrix multiplication with tensor cores. Now we get something fast, right? Well, if you run this, and this is basically, again, like how it would look like if you run it in our course tester, we get a result. Okay, this is something like 15,000 large matrices, 1.5 seconds. That's a very large matrix. That's not that long. Maybe that's actually good. 4,000 gigaflops. Well, that's why you always need to do a speed of light analysis, right? Like if you actually look into the spec sheet of this GPU, which unfortunately it only shows the tensor performance, which I think in this case is FP16 tensor performance. So there's another factor of 2 that you need to add to go to the performance of int8 tensor cores. Then we're actually orders of magnitude away from what we're supposed to get. So apparently it's not quite that simple to get decent performance, even if you're using tensor cores. So what's going wrong? Well, there's this fantastic slide from Stephen Jones's GTC presentation. I'm not sure if you can read the scribbled out part, but it's how GPU computing works. And basically, in the very beginning of his talk, he changes that to basically the most important question about making this work: where's my data? And a lot of this presentation is also just going to be like putting data in the right places at the right time, so that the GPU can actually do its job and go bull. So what went wrong in this simple example? Well, basically what we have is a bad memory access pattern. This load matrix sync function, in this case, fetches data from global memory and distributes it across the different threads in a warp in this unspecified manner that this big warning was talking about. And stores these parts of the input in registers of CUDA threads. Like it's the normal registers that you also have if you do regular CUDA, nothing special here. Which also means that the normal considerations of load performance apply. Like the access across matrix B in k-dimension that we do is strided because we've declared B to be row major. And that means we get uncoalesced reads, and uncoalesced reads are very much terrible for performance. So how do we fix this? Well, maybe let's look at the graph first. Like, so this is now taken from Nsight Compute, the memory graph, which is one of the first things, I guess, to usually consult when figuring out how to improve a kernel. And we can see basically like we're transferring a lot of data like for this matrix multiplication. Like between L2 cache and L1 cache, there's 630 gigabytes of data transfer happening here, and 206 gigabytes of data transfer between device memory and L2 cache, which is quite a lot if you consider this GPU has, I'm not sure, 8 or 16 gigabytes of memory. So very much many times over the entire memory of the GPU that gets read over and over again here. And then if we look at the second type of performance indicators that you get with NCU, which I think you always should look at, and which is the warp stall cycles. Maybe I should explain what those are, because I guess not everyone is familiar with these. So basically what this tells you is every cycle for which the warp actually did instruction, like how many different cycles did it spend in some state where it didn't do anything useful. And basically, now these are the top contenders, where the first one is stall LG throttle, which basically means like the warp wanted to start loading new data from global memory, but there's a limited amount of data that you can wait on in your GPU. So the warp couldn't actually do this load instruction. It had to wait for some data to arrive before this new load could go through. And that's really, really terrible for performance, because it also means that you can't hide this latency, because the load doesn't even start until you process this instruction. The second most important contribution is stall long scoreboard, which is that the load instruction went through. We requested this memory from global memory. But then at some point we wanted to actually use the data that we requested, and it wasn't there yet. Which means that at least we could do some sort of useful work between the point in time when we requested memory and when we tried to use it, but we didn't actually have enough useful work in between to arrive at this point in the instruction stream where we wanted to use it, where the data was already available to process. And basically, the successive versions of this kernel, they're trying to really get rid of these things and push them to as close to zero as possible. So now for fixing this, the idea is quite simple. The problem was that both matrices are in row major, but we want to have like nice linear access pattern in both matrices. So if you don't have any transposes in your matrix multiplication, that means that the second matrix should be in column major format. And then basically the only thing you have to change is this definition of the Y fragment and the indexing in load matrix sync. But now we actually need the second matrix also in column major format, which means that we have to run an additional kernel that transposes the matrix. And again, like if you think about it, like this kernel is also going to be terribly memory bound. So why is that a good idea? Well, it goes back to, again, this big O notation, right? Like the size of the matrix is n squared, whereas the cost of matrix computations, matrix products is n cubed. So for sufficiently large matrices, like the ones we're looking at today, this transpose is going to be really, really cheap compared to the actual matrix multiplication. Like in this case, 6 milliseconds compared to, well, the original version, basically 1.5 seconds, the version with the column major second matrix just below 1 second. So several orders of magnitude faster. We don't really have to worry about the overhead, at least with this slow kernel yet. And then if we go back to NCU and now also use this nice feature that you can show the difference between two kernels, then you can see that we've improved quite substantially on the amount of memory that we read. And also, the first thing is the amount of memory requests we do decreases by an entire 60%. There's some like buffering or some way the cache has shielded the L2 cache from this. So it doesn't translate to a 60% decrease in transfer between L1 and L2, just a 30% decrease, and then again like a 40% decrease in transfer between device memory and L2 cache. So very much took quite a bit of strain off the memory system with this very simple transformation. Now, interestingly, if we look at these warp stalls, like maybe to make this more interactive, like what would you expect to happen with warp stalls now that we fixed this memory access pattern? Like, I guess, Mark, you have to look at the chat now and tell me if someone writes something.
I'll take a look.
If no one is doing anything, you can also give it a try yourself.
So Phil is saying, so Marwan is saying shorter stall durations.
Yeah, that's kind of also what I initially would have expected, right? Like because we're no longer having this big memory problem. But it turns out actually it gets more, which seems very counterintuitive when you first look at this, especially since we actually know that the kernel got faster. And the really important thing when looking at these statistics is that they are normalized to how many cycles did you spend stalling relative to the amount of cycles that you actually did useful work. So if we look at one more of these sections that you can get in NCU, which shows you which instructions were executed. We actually reduced the number of instructions by 45% because now we are using far more load instructions, and also we need far less index calculations, which are these imat and iadd instructions that you can. By the way, can you see my cursor? You can see here.
I cannot see your mouse, no.
Okay, so it's the top two entries here. Those are the index calculations. The one after that is the LUG load from global memory. And I think the one SHR shift right is probably also from index calculations. So all of these go down, which means that the denominator in the normalization of warp cycles, like the number of cycles in which we issued an instruction, has also decreased quite a lot. So that's why this ratio didn't actually improve, even though the kernel got a lot faster. Okay, so at this point, maybe we should get out our standard kernel optimization toolkit that you have available now if you've read, for example, the PNPP book, and try to apply some of the standard techniques to improve this further. So basically, the first step that for these types of kernels that reuse conceptually at least like the same data over and over again, like we saw we were reading much more memory than the GPU has, so is to make sure that we are using this memory in the right place of the memory hierarchy. And I guess you've all seen the figure on the left, but to be honest, I'm not super happy with that figure because kind of like all the interesting stuff is happening just at the tiny top of the pyramid. So the right figure from some NVIDIA blog post is maybe a bit more helpful, which shows that, yeah, you have this global memory, then you have the L2 cache that you also saw in the NCU things. And then inside each streaming multiprocessor, you have still two different versions of memory. One is registers, which is the only memory that actually is very fast, and the L1 cache that's at the same time since Volta, I think, also shared memory. So now the idea is to move as much of the memory access to this faster memory. And for that, we start, of course, by trying to reuse in the fastest memory that we have available, which is registers. And there, the idea is also quite simple. Instead of calculating just a single fragment, so a 16 by 16 result with each warp, which corresponds to 8 outputs per thread, we switch to each warp handling 3 by 3 fragments as models. Which means that we need to load 6 input fragments, like 3 for A, 3 for B, and we get 9 output fragments. So in an arithmetic density in kind of like units of fragments loaded to output fragments calculated, we've improved by a factor of 3 in terms of data reuse that we get from this. And I think in the PNPP cookbook that would call this thread coarsening, even though maybe in this case the more accurate thing might be warp coarsening. Anyway, like the main point here is to reuse memory as much as possible in registers, and the only way you can do that is if each thread handles more of the output results. So in that sense, both these strategies kind of like are just the same thing from different perspectives. And then the procedure is exactly the same as when you optimize a scalar matmul kernel. So basically, what you do is in the beginning of your loop, you load the 3 results that you want to have for one of your fragments, and then in the main computation loop, you load the second one that you want to combine with these 3, and then you have this now nested inner loop that goes over the preloaded Y fragments and does the accumulation in the V accumulator. Yes. So if we then again run this and look at the first, again, like the memory chart, we get another 60% reduction, or almost 70% reduction in the amount of memory requests we do, and 50% reduction in memory transfers, basically. So now this is relative to the already improved kernel with the column major B matrix, not towards the first one, because if we kept using the very first one as our baseline the numbers would just go into a not like 99% range, and we wouldn't actually see the difference between the faster kernels. So every NCU comparison I'm showing will be between the previous kernel and the next one, and not with a fixed baseline. Finally, we also get this reduction in long LG throttle warp stalls by basically a factor of 1/2. And interestingly, we still get decreases in the amount of instructions that we need to do, because we know once we have these fragments in registers, for registers you don't need and you even can't do address calculations, because registers have to be fixed at the assembly level. So a lot of this address calculation arithmetic on integer cores also goes away. Like the, again, iadd3 and imul or imat instructions. And also we do, again, fewer global loads, of course, because we reuse the data at the level of individual registers and threads. Now, the question is, does this have any drawbacks? And again, maybe this is also one of these questions that someone from the audience could jump in and give an idea.
I guess while people are thinking, Alex is asking, just to clarify, so far none of this is specific to int8 or Turing architectures, right? As this is just generically for devices that have tensor cores.
Almost. Like some specifics are different, like the amount of, at the danger of spoiling the question I just posed, the amount of registers you need to store results and inputs, right? Like that changes depending on whether your inputs are 32-bit floating points, 8-bit integers, 16-bit numbers. But otherwise, yes, like that's one of the main kind of messages maybe I want to take you to take home from this, is that everything I'm doing basically is exactly the same recipe as you would do even with just like a regular scalar matrix multiplication without tensor cores. It's just that we kind of like shifted our perspective from looking at individual numbers to looking at these 16 by 16 groups of numbers. But once you do this shift of perspective, it's exactly the same thing. And of course, also on other GPUs, it might not exactly be like 16 by 16. It might be a different shape. And even on Turing, you can use different shapes. But like the square one is the easy one, I think, to explain.
So it sounds like the issue is you increase register spillage?
Yes.
Like...
Well, at this point, it's not yet spilling. It's just the amount of registers that you need per thread increases, so the amount of threads you can have at the same time goes down. So we're not in spilling territory yet. We're in occupancy, like reduced occupancy. And of course, that means that the kind of like promised automatic hiding of latencies that you get with these oversubscribed GPUs, that gets less effective. But since we have so much less latency to hide in the first place, this is very strongly a net win to this thread coarsening / register reuse. But it means that we can't really keep playing this game much further, because if we then go to like a 4x4 reuse, for example, the amount of registers increases much more. And then we might get into the register spilling territory. But of course, like if you remember the graph from earlier, there's one more memory in this SM that we haven't used yet. Did you want to ask a question, Mark?
I did want to ask a question. So how come you started with 3 fragments? Like, I guess you spoiled the answer with like more than 3 would give you the occupancy problem. So why not do 2 as your start?
Well, I mean, you can start. I mean, that's kind of like part of what you're doing when you actually develop these kernels, right? Like you would not, at least I would not write this code exactly like this. I would have like a const expr tile size equals 3 somewhere in the beginning, and then every 3 here would be tile size, but that would make the text longer on the slide. So I converted this to explicit freeze. And then you basically try to figure out like what's, and that's also, it's not something that you necessarily can predict. That's also where benchmarking comes in, right? Like you try Like you can probably predict that 3 is better than 2. You might not necessarily know whether 4 is better than 3. And then there's also not necessarily, like you don't have to use square shapes, right? Like maybe 4 by 4 runs out of registers, but if you could do 3 by 4, maybe that gives you enough registers. Yeah. And this is also not necessarily the end of how you can do register reuse. So I won't get to that point in this talk, but essentially, like after you fix lots and lots of other performance problems, at some point the register reuse actually ends up being a bottleneck again, and then you need to go to even larger sizes, which means that this automatic latency hiding really almost goes away because you can't have more than one block on the GPU anymore. So any kind of sync threads call that you do is really a complete hold of the GPU. Like nothing is going to happen in all the threads that are finished yet. And that would be a very bad state maybe to start working with shared memory. So it's nicer to do our first shared memory experience with a setting where you can have more than one block so that sync threads is not such a performance killer to start with. Maybe that's it's also just like at some point, like you write some code and it follows a certain trajectory, but it doesn't necessarily mean that all the optimizations I'm doing have to be done in the order I'm presenting them now. Like you can probably mix and match, like not everyone, because some like unlock new optimizations or new bottlenecks that need to be fixed, but some of those are interchangeable, and the order in which you do them doesn't matter very much. But generally, I would recommend the first thing to do is reuse in registers if it's possible, simply because registers are so much faster than even shared memory, which is also something we'll see in a couple of slides, I think. Yeah, so now we want to reuse data in shared memory, and kind of what I said, like if you look at the title of the slide, I've put the fast in quotation marks because once you actually get down to it, especially for something like matmul, you notice that shared memory isn't actually as fast maybe as you think when you're first told about it. So for simplicity here, again, like this is one possible choice. It's not necessarily the best or the only choice you can make, but let's say we use 9 warps per block and basically like 3 by 3 tiles or 3 by 3 tiles, so that in total one GPU block handles like 3 warp level tiles of 3 fragment tiles of 16 elements each. So basically 144 by 144 is the size of the result fragment that gets calculated by a single block. And then one nice thing we can do, again, like assuming that the input is nice enough that everything is well aligned, is we can actually load the data into shared memory using these vectorized load instructions. So in this case, there's a bit of a hack going on because you don't get, like NVIDIA gives you basically vector types from 1 to 4 elements, but in order to actually use fast vectorized load instructions, you need 16 bytes. So, and there is no int8 16 data type or byte 16 data type. So instead we pretend that we have just an int4 and load this as an int4, which is the number of bytes that we want. And then again, for writing it to shared memory, we again do this reinterpret casting, pretend that the memory location that we write to is int4s. And basically what this does is it tells the compiler that the int4 data type not just has the information that it's 4 integers, it also has the information that this int4 has to be at a 16 byte boundary. And this memory alignment is what allows the compiler to choose these faster load instructions for this data type, or faster store instructions when you then write it to shared memory. Yeah, so basically, at this stage, we don't really care about the assignment of individual blocks to threads. Like each thread just is loading some sort of like linear part of the memory, and we are transferring this, basically copying it verbatim to the shared memory. And of course, this is one of the points where newer GPUs could do fancier stuff. Like in Ampere, you get these asynchronous load and store instructions, and this entire process of taking a submatrix and moving it from main memory to shared memory is basically what the tensor memory accelerator that is new with Hopper and now in Blackwell, I think, is designed to do without you having to actually do manually anything or using your CUDA cores for this, like having it directly in hardware. And of course, that makes it much more efficient. But in Turing, this is the way you do this copy. Like that's the trade-off. Like you don't have that many features, but it also means you don't have to worry about asynchronous or anything. It's just the regular CUDA code that you get. And then, of course, you would have the same code for the second input matrix, which I'm not showing here. And then the actual loop that does the matrix multiplication is basically the same, except that now the addressing, like where you're doing your load matrix sync from, is the right address in shared memory. And maybe something to keep in mind is this last argument to this function is the offset. Like if you go from one row to the next, how many elements do you need to go? And now that we only have this small single tile in shared memory, that offset has changed from being the number of columns in the matrix to just the fixed constant 16, like the size of the fragment. But otherwise, the code still looks the same. And again, we get this very drastic reduction in amount of memory that we need from global memory. So in terms of the load instructions, we have now an 80% reduction. So if you remember, we had a 60% reduction of that. We had another 60% reduction, and now we have an 80% reduction of that. So we're now several orders of magnitude, I think, or at least like 1.5 orders of magnitude better than the original kernel. We're also down to just transferring 9 gigabytes of memory from device to L2 instead of several hundreds. Does anyone notice anything problematic in this memory chart? Like anything that you might not have expected, or anything that you think might actually hurt performance here?
Phil is suggesting the plus 600% to L2.
Yes, and what's the reason why we get that? There's an even worse number than 600%. If you look to the left of this graph, like what's causing these 600% to L2? Okay, so far we've looked at this top connection that goes to global memory. If you go one down, there's local memory. And suddenly we have plus infinity% of local memory usage, which probably isn't very good. And so again, like, do you know what the reason for this is? Like the immediate reason, at least. Like, what does it indicate?
So this is like a guess, but like basically you're putting too much stuff in your L2 cache, and L2 cache you're not explicitly programming. So this really suggests that this is spillover from your L1 cache, which really means that like you're putting too many things in shared memory in your code. So this also suggests a form of spilling.
Yes, but it's basically what we talked about. It's now we get register spilling, and register spilling goes to L1, but L1 cache is write through, so everything that you write to L1 has to be written to L2. So all the spilled registers actually get written to L2, and that that's this 600% increase that we see. And this is one of these kind of like weird cases where we didn't actually explicitly use any more memory, like we didn't make the tile size larger, but for some reason the compiler wanted to use more registers. I think it might be actually that in this case I deliberately set the I told it I need to have 2 blocks instead of 1 to ensure that this sync threads doesn't block the entire kernel, and that limits the amount of blocks that you can have concurrently, of registers that you can have per block. And then we got this register spills, which isn't great, but Okay, yeah, now it's actually highlighted also. But again, like we're doing trade-offs here. So if we get an 80% reduction or almost 90% reduction in what we read from the very slow device memory, maybe this larger spillover to L2 cache, where you have to think like most of the reading that happens of these spill registers actually happens from L1 cache. It's just that they have to be written to L2, but we're not reading them from there. That this is very much a worthwhile trade-off. So again, looking at the other performance indicators in an NCU, we basically, like one thing that we get that we didn't have before is this barrier stall, because now we have sync threads in there, and threads have to wait for other warps in the block to arrive at this barrier. But on the other hand, the bar for LG throttle has diminished by, I don't know, like a factor of 5 maybe. The long scoreboard, like the waiting for results from global memory, has also decreased by more than a factor of 2, which is very nice. And like in terms of the instructions, we've also seen some changes, like some more address calculations now for the shared memory, and we have this new LDSM, the load from shared memory matrix instruction, and instead not many LGG, like load from global memory instructions. But one thing I want to highlight, oh no, it's not on this slide yet. Okay, but trying to remember if it comes later. Okay, I'm hoping it comes later, otherwise I have to remember to mention this. So let's look at maybe first at where we are with the optimized kernel that we have. So extending the table from earlier, with the register use and shared memory kernels, we get very nice speedups in terms of the just wall clock time of the kernel. So we are more than a factor of 4 faster than the original, which is, I think, a pretty nice improvement, considering that we really haven't done anything fancy. Like we have just applied the kind of standard toolkit that you get from, for example, PNPP. So what's the new bottlenecks that we just saw in this? So one thing that I wanted to highlight, yes, exactly, in this slide is these stall Mayo throttle and stall short scoreboard, which didn't appear in the earlier kernels, which is this is basically the evidence for my claim that shared memory isn't actually that fast, because stall Mayo throttle is basically the same thing as the stall LG throttle, except for shared memory. So that means that you wanted to load something from shared memory, but shared memory said like, oh, I have still like 10 loads I have to do. I can't accept any more requests right now. You have to wait. And stall short scoreboard is that you managed to make your request to shared memory, but you wanted to use the result before it was actually available.
Erik, I have a few questions. Like, what does this terminology really mean? Like, what does Mayo mean? What's a scoreboard? I'm wondering if you could just share a bit more detail.
I think that's maybe someone from NVIDIA needs to explain, because I'm also not completely sure. Mayo is memory I/O.
Memory I/O.
That's something I can tell you.
I see. Okay, that makes sense.
But yeah, I've also like looked at several Stack Overflow answers and NVIDIA forum answers to really understand some of these, and I'm not confident I understand all of these.
Well,
but yeah.
All right, sounds good.
You said you had several questions, or just this one?
Just this one on the terminology.
Okay, great. Yes. So now to do further optimizations, basically, it's still the same story. We want to work on our data, but now we are kind of like.
We still have a question from just popped in from Alex. Is Mayo about GMEM to shared memory, or shared memory to register bottlenecks?
Mayo is shared memory to registers. Long scoreboard or LG throttle is registers to global memory. And I'm actually not sure what well, I guess the like async loads, they don't actually generate warp stalls, because by definition they're async. So you will just stall by waiting on the explicit barrier that you have. So those wouldn't have anything different, I guess.
Okay, I'm seeing a lot more discussion on this. So Dongyan is saying, couldn't shared memory conflict also have caused significant MIO throttle?
Yes, because shared memory conflict means that the shared memory needs more cycles to fulfill your requests, which means that the queue of outstanding requests gets cleared more slowly. So any new incoming requests have to wait, right? Like,
all right.
Yeah.
I also see a bunch of comments from Vikram. Maybe let me just invite him. That might make things easier.
Yeah.
Give me a second.
Yeah, I hope I haven't said anything that's too far from the truth. Let's maybe stay on the slide. Yeah, but basically, the next part of the talk will then be something that maybe is no longer just standard PMPP techniques. So this is actually a very good point to have this discussion, maybe.
All right. While Vikram's joining, maybe we can keep going. I don't know how long he'll take.
Okay. So basically, what we have right now is that this load matrix sync does this unspecified mapping of memory locations to registers every time we load in this inner loop when we read from shared memory. And of course, this could be shared memory bank conflicts. It's also simply maybe that these things aren't nicely vectorized. So the question is kind of, can we avoid having to redo this like memory location to register mapping every time? And this seems like it might be not possible because the warning I read out earlier, like the mapping of matrix elements into fragment into storage is unspecified and subject to change in future architectures. Like that basically says like, well, you have to do this mapping. It's and you can't assume anything about this mapping if you're using the like high-level C++ API. But I'm now making this very bold assumption that the layout does not change while you're running your program. Like otherwise, I think nothing could work. So I think that's a very fair assumption. And that basically means like what we can do is use this load matrix sync to get from memory layout to register layout once, and then just have some operation that maps registers to memory in a linear way that we can then easily load from again. So basically, these two helper functions that maybe would be useful to have in the MMA interface, which is really just taking the like frag.x. This .x is just the internal memory of the fragment of the current thread, and we're just and that's 64 bits, like an int2, and we are just verbatim like taking whatever is in these bits for this thread and storing it in a linear location in memory. We don't care which matrix element that maps to, we just do a blind copy of this. And then for loading, again, we just restore exactly the location where we store to this fragment.x, like in the register mapping, again, without having to know the correspondence to matrix elements. And since these two functions are the inverse from each other, we can use the MMA load direct function that I've defined here to load data from shared memory, where we have guaranteed linear memory access pattern, which can be faster than whatever the MMA load function, MMA load sync function is doing.
All right, yeah, we actually got Vikram to ask some, to maybe correct some stuff. Hey, Vikram.
Hey, sorry about I was in the chat and I was trying to talk over there. Sorry about that. So there was a question regarding MIO and scoreboard. And also there was a question regarding where can I find this information. What I did was I just did perplexity search and I got the information from the links to. So for some reason, I cannot share the location where this is in the chat because it's not allowing me to send a message here. So I need to figure that out. But here is the thing. MIO is a primarily responsive for memory-related task. Erik, you are right over there. things like load store init, address translation units, or the divergence manager, or any of those, they fall under the MIO category. Scoreboard is mainly to handle hazards. In the typical classical world, in the CPU side, you had the read after read, read after write, write after read kind of hazards that you have to manage. So those comes under the category of scoreboard on how to determine whether there are instruction hazards that can actually happen or not.
Okay, thanks. And feel free to jump in at any time when I'm presenting these NCU graphs if you have something to contribute, I think.
Sure,
there's a lot of interesting stuff going on, maybe. Okay, yeah, so basically, like, this is our way of cheating around this constraint that we're not allowed to know what's inside a matrix fragment. We just do our blind copy without ever looking at the mapping of registers to thread indices. And basically, then the only change we have to do is we, when we are writing to shared memory, we do this load sync that does the register mapping, and then we use the store direct to write to shared memory. And then inside, I guess the highlighted line should be one below. Inside the main loop, we now use these MA load directs. And by the code we've written here, those are now guaranteed to at least use like twice vectorized load instructions instead of loading just whatever MMA load direct is using as granularity. And now if we look at this graph, now this is where things get a bit more interesting because we have like these some things going up, some things going down. So one thing we can see is like we haven't actually like on a high level, the code hasn't changed in the way it's using explicitly managed scratch memory. But for some reason, all these register spills go away, which I think is simply because we have this much more nicer addressing scheme. So the compiler doesn't need as many scratch registers to calculate addressing information. And we now go back to a reasonable amount of writing to L2 cache. We also, interestingly, get this 100% increase in reading instructions, which, if you remember from the earlier version, we were doing this verbatim copy from global memory to shared memory using these vectorized instructions. And now we are using this unspecified size type read MMA load sync instruction, which isn't as vectorized as our initial as our copy code was. So that's why we get more instructions here. But now if we look at the actual timings we get, we see that this LG throttle basically goes away almost completely. Like we no longer have the situation where we want to submit a load instruction and can't. We also see that the MIO throttle and short scoreboard is reduced drastically. But we pay for this by having more long scoreboard stalls now. But I think, again, part of this is also because we have fewer instructions necessary to calculate addresses, so the denominator may have changed. But one thing is that we are no longer in this regime where we can get like massive speedups with simple changes. So in this case, this optimization is only at a like 7% speedup and no longer like a 2x that we could get with these early optimizations. Yeah, I think the LG throttle might just be the register splitting. Like that would have caused lots and lots of load global instructions to be, or I guess load local in this case instructions to be generated that now have vanished. But that's not the end of the pre-processing, kind of like pre-shuffling that we can do. Because similar to transpose, this shuffling also is just something that reads the matrix once and writes it once. So it's an O(n) squared operation. So instead of doing this every time we write the matrix to shared memory, we could also do this in a separate kernel that we run in front of our main matrix multiplication kernel, where we just make a copy of the matrices that is in this linearly addressable memory format. And this would be the example for handling matrix A, but matrix B would be kind of the same thing. So it's really just this load sync store direct that we had in the shared memory part now move to a separate kernel. And then the actual gen kernel gets even simpler, because now we can also use the MMA load direct when we are loading and writing to shared memory in the first half of the main loop. And the inner part of the loop actually doesn't change at all, because we haven't changed the way our data is laid out in shared memory. And now with this optimization, we are back to the old value of the number of requests from global memory, and nicely the transfer between caches and between cache and main memory also decreases. So from a memory perspective, this was very much a win. If we look at the warp stalls, I guess it's a bit more unclear whether this really helps, but the LG throttle was reduced even further. I'm not completely sure why short scoreboard goes down here. Like, this seems more like a very noisy indication. So yeah, I can't give a precise interpretation for all of these changes here. But then if we look into the instruction statistics, we see that we've reduced the number of instructions by 20%. Like IMAD again, like address calculations go down. I add address calculation, some shift. So I think the main speed up probably comes from the reduced amount of address calculation necessary in the inner kernel. And one thing also that I maybe should mention is in this definition of this helper function, which was more like an accident when I first wrote it, because all the NVIDIA functions explicitly say like they're warp synchronous. I put this sync warp in the end. I don't think it's needed for correctness. It causes the compiler to emit these weird knob instructions that you can see showing up here quite often. But then I tried removing that, and in many cases, actually the performance reduced. And I think that might have just been because the sync warp acts also as a barrier for the compiler to reorganize some of the loads, and it might want to move loads later in the instruction stream to save registers if you don't have that there. And by forcing it to load early, you remove the amount of scoreboard stalls that you get. But I'm not completely sure about the exact effect this has. Yeah. Okay, and now maybe for closing this talk, like let's look at again, like where are we in terms of like speed of light analysis, which is basically in this case, like speed of light would be using 100% of the tensor cores, and we're actually pretty far away still. Like this is more like 40% utilization of tensor cores. In terms of timing, though, we've made quite a lot of progress. So we are at 178 milliseconds now, plus the 11 milliseconds for pre-processing. And we can also see like we got 5 additional milliseconds for this reordering of data, but we got more savings from making the kernel faster. So this additional pre-processing kernel still is a net win in terms of timing. And both because I guess this talk was already an hour, and also because I simply didn't have time to prepare more slides, the further optimizations are in the Outlook slide now. So what we would be doing next would be double buffering to reduce these long scoreboard stalls. At this point, then we can start looking at larger block sizes because we are no longer that strongly suffering from the sync threads synchronization. Then you could also increase the amount of vectorization because we had been using these int2 instructions, but you could go to int4. And in the end, the last version would be something like carefully trying to really organize the instructions to like manually hide whatever latencies you can see if you look at the like SAS view in NCU, where it tells you exactly like at which instruction which stalls were happening. And if you're interested, I can make a part 2 at some point that kind of like continues from there. But at this point, maybe my main request to you is maybe try it out. Like it's very new, this exercise, so there might still be some bugs or problems. I would be very happy to hear if you encounter these, or Also, if you get stuck trying to solve this, just shoot me a message on GPU mode, and also feel free to try the like AVX 512, AVX VNN type versions of this exercise. Yes, and that's basically my talk for today. So if you have any more questions, I'm happy to discuss more.
Excellent. Yeah, thank you, Erik. I think I'm already seeing people want the part 2. I certainly want one. So Erik, Alex is asking, will you be sharing code for the prior examples and further optimizations? It would be super helpful, especially for some of the last slides.
I don't want to share complete codes because I think the main learning effect comes by trying to do that yourself. Like I can share the slides with these like half-baked code examples where maybe you need to figure out some of the indexing yourself still. But I don't want to share like something that you can just copy and paste in the exercise. Like I think that kind of goes against the spirit of the exercises. Yeah.
All right, excellent. So if folks have any other questions to Erik, you know where to find him on Discord. I will say that like today, Erik discussed a lot of like different like details and profiling. So next week is going to be interesting because on Friday at the regular time, we have like the NVIDIA chief profiler architect who's going to come give us a talk. So if you're like, why is this called MIO or why is this called the scoreboard? This is the person to complain to. And then on Saturday of that very same week, next week, we're going to have Pranjal SSH, who's going to be giving a very similar talk, but applying it to H100s. So it's going to be very much a sort of similar in spirit. So if you enjoyed this talk, like I'll bet you'll enjoy the 2 talks that come next week. So yeah, Erik, thank you so much. This was great. But by the way, I got an early preview of the course that Erik's pitching. It's extremely instructive. Like there's sort of a lot of problems, very profiling heavy. I don't quite know of like a CUDA course that's quite like it. So if you're interested in having problems that you can work on throughout the week, highly, highly recommended. And yeah, with that, we'll see everyone next week. Thank you, folks.
See you.
All right. Erik, just stay for 1 second.